Good morning, students. Last class we are completing addition of scientific notation, subtraction of scientific notations. In this session, in this class, we are completing another two arithmetic operations, that is multiplication of scientific notation, division of scientific notation, division of scientific notation. First one, students, multiplication of scientific notation, multiplication of scientific notation. To multiply the numbers in scientific notation, we are using the following numbers. We are using the following formulas, that is 10 to the power of x into 10 to the power of y is equal to 10 to the power of x plus y. 10 to the power of x plus y. Once again, student, to multiply the two numbers in scientific notation, we are using following formula or following relation, that is 10 to the power of x into 10 to the power of y is equal to 10 to the power of x plus y. In lower classes, we know that, students, if bases are equal, powers are added. If bases are equal, powers are added. 10 to the power of x into 10 to the power of y, bases are equal. Therefore, 10 to the power of x plus y, 10 to the power of x plus y. Remember, students. Next one example: 2.4 into 10 cube into 5.6 into 10 to the power of 5. Both are scientific notation. Here the bracket indicates we are multiplying these two scientific notation. For multiplication, very easy, students, like normal multiplication. What is the procedure we are using? Same procedure, only we are using. That is, all the numbers one side, that is 2.4 into 5.6 into 10 cube into 10 to the power of 5. 10 to the power of 5. All the numbers one side, all the powers one side. That is 2.4 into 5.6 into 10 cube into 10 to the power of 5. Into 10 cube into 10 to the power of 5. We know the, students, 2.4 into 5.6, 10 to the power of 3, 10 to the power of 5. According to formula, 10 to the power of x into 10 to the power of 5 is equal to 10 to the power of x plus y. Here also, that is in the same form. 10 to the power of 3, 10 to the power of 5, 10 to the power of 3 plus 5, that is 10 to the power of 8, that is 10 to the power of 8. We know the, students, 2.4 into 5.6 equal to 13.44 into 10 to the power of 8. 13.44 into 10 to the power of 8. It is the answer of the multiplication of the two scientific notation. Remember, student, if the final answer is not in a scientific notation, we can convert the following number into scientific notation. We can convert the following notation into scientific notation. For example, students, here 13.44. This number is greater than 9.999. Hence, the decimal point moves towards left until there is a single non-zero digit before decimal point. And if the decimal point moves towards left by one places, 1 is the power of the 10. 1 is the power of the 10. That is 1.344. 1.344 into 10 to the power of 1 into 10 to the power of 8. It implies 1.344 into 10 to the power of 9. Why? Because 10 to the power of 1 already 10 to the power of 8, that is 10 to the power of 9. The final answer is 1.344 into 10 to the power of 9. 1.344 into 10 to the power of 9. Similarly, students, division, same formula we are using. That is, to divide two numbers in scientific notation, we are using the following numbers. To divide the two numbers in scientific notation, we are using the following numbers, student. That is 10 to the power of x by 10 to the power of y is equal to 10 to the power of x minus y. 10 to the power of x minus y. Here 4.74 into 10 to the power of 12 by 6.82 into 10 to the power of 20. 10 to the power of 20. Same procedure, all the numbers one side and all the powers one side. That is 4.74 by 6.82 into 10 to the power of 12 by 10 to the power of 20. It is in the form of 10 to the power of x by 10 to the power of 5. 10 to the power of x by 10 to the power of 5. According to formula, if any form in the form of 10 to the power of x by 10 to the power of 5, then that becomes 10 to the power of x minus y. We know, the students, that 4.74 into 4.74 divided by 6.82, nothing but 0.695, 0.695, and it is in the form of 10 to the power of x by y, 10 to the power of 12 minus 20, 10 to the power of 12 minus 20. Therefore, 6 minus 0.695 into 10 to the power of minus 8, because 12 minus 20 equal to minus 8. Since it is not in the form of scientific notation, the final answer is not the scientific notation. 0.695, that is less than 1.000. Hence, the decimal point moves towards right according to concept. If the decimal point moves towards right one place, then -1 is the power of the 10. That is 6.95 into 10 to the power of -1 into 10 to the power of -8 into 10 to the power of -8. 10 to the power of -1 and 10 to the power of -8 nothing but 10 to the power of -9. Hence, the final answer of the division of the following set of numbers is 6.95 into 10 to the power of -9. 6.95 into 10 to the power of -9. By using these two formulas, you can multiply and divide the number. And remember, students, the final answer must be in scientific notation only. Okay, students. Next continuation topic, student, significant figures. Significant figures. Before discussing that, some introduction part is required, student. That is, every chemical experiment, every chemical measurement associated with some error, with some mistake. The error present in the measurement can be due to the following factors. One is skill of the observer, another one is defect in the measuring device. Defect in the measuring device. Every chemical measurement associated with some error. The error present in the measurement can be calculated by using two factors due to the following reasons. One is the skill of the observer, another one is defect of the measuring device. I will explain, student. Skill of the observer. For suppose we are measuring the piece of chalk. We are measuring the piece of chalk. If the person is not a skilled person, he is not measure the piece of chalk accurately. Hence, he will get error and wrong measurement. Similarly, measuring device, defects in the measuring device. For example, we are measuring the thickness of the rubber ball by using the vernier calipers, or we are measuring the thickness of the copper wire by using the screw gauge. In the screw gauge or vernier calipers, any defect is there, that instrument, that measuring device is having any defect, then definitely that measurement will be having error, that measurement will be mistake only. That is, the mistake or error present in the measurement due to the two factors. One is the skill of the observer, another one is defects present in the measuring device. Defects present in the measuring device. To give the result of the experiment in an accurate way, some digits are required. The digits are known as significant figures. To express the final result of the experiment in an accurate way, some digits are required. The digits are known as significant figures. The digits are known as significant figures. Hence, these significant figures are required to express the result of the experiment in an accurate way. In an accurate way. Even though skill of the observer is there, even though the measuring device is having some defects. Measuring device is having some defects. What is the significant figures we are discussing, student? In this topic, we are discussing three main topics, three main subtopics, student. What is significant figures? What are the rules for calculating significant figures? Arithmetic operation during the significant figures, like addition of significant figures, subtraction of significant figures, multiplication and division of the significant figures. These three subtopics we are discussing. Right, students, we are entering into topic. First one is, what is significant figures? What is significant figures? Definition, students: the meaningful digits which are known with certainty plus one uncertain digit are known as significant figures. Are known as significant figures. Once again, students, the meaningful digits which are known with certainty plus one uncertain digit are known as significant figures. Are known as significant figures. The definition can be clearly explained by using some example. That is this one. Piece of chalk length is 2.75 centimeter. Piece of chalk length is 2.75 centimeter, which can be measured by using the scale calibrated from 1 centimeter to 3 centimeters. 1 centimeter to 3 centimeters. You know, the students, our normal scales are calibrated from 1 to 15 centimeters. To measure this piece of chalk, I am considering small scale, which is calibrated from 1 to 3 centimeters. 1 to 3 centimeters. We know that 1 to 2, 1.5 is present, 2 to 3, 2.5 is also present. The length of the piece of chalk is exactly 2.75 centimeters. 2.75 centimeters. You can measure like this, students. The length of the piece of chalk is up to here 2.5 centimeters. Here 2.6 centimeters. Here 2.7 centimeters. By using this scale, we can measure the length of the piece of chalk up to 2.7. But here 5 is also given. That is in between. Here it is 6, it is 7, it is 8. In between 7 and 8, the 5 will be present. In between 7 and 8, the 5 will be present. But exactly where is the 2.75 is not possible by using this calibrated scale. Because the reason is here they are mentioned 2.5, 2.6, 2.7, 2.8, 2.9 and 3.0. In between the 2.7 and 2.8 they are not mentioned. They are not mentioned. Hence, it is clear that the piece of chalk length is 2.75 centimeters. 2.75 centimeters. And remember, students, it is the length of piece of chalk 2.75 centimeter. The first two digits 2, 7 are called certain digits. Certain digits. Why? Because 2.6, 2.7 they are accurately measured by using this calibrated scale. Hence, 2, 7 are certain digits, that is measurable digits. Whereas that 5 is a doubtful digit. There is no clarity. There is no confidence that is 5 is correct or not. That's why this 5 can called as the doubtful digit. Because of this reason, this digit can be also known as uncertain digit. Uncertain means it may be 2.7, no, it may be 6 or 7 or 8 or sometimes 4, 3 or 2. Any number will be possible. Up to 2.7 your answer is correct and 5 is not correct. It will be doubtful digit. It will be uncertain digits. Therefore, student, 2, 7 are certain digits. 5 is the doubtful or uncertain digit. In every number, the last digit is the uncertain digit or doubtful digit. Therefore, students, now we can discuss definition once again. The meaningful digits which are known with certainty plus one uncertain digit are known as significant figures. In this 2.75, student, certain digits are 2, 7 which are known with certainty plus one uncertain digit, doubtful digit are known as significant figures. Hence, 2.75 contains 3 significant figures. 2, 7, 5 are the 3 significant figures present in the measurement 2.5 centimeters. 2.5 centimeters. The main purpose or theme of the significant figures is to express the result of the experiment in an accurate way, in an accuracy way. Why? Because 2.7 centimeters and 2.75 centimeters. 2.75 is the more accurate when compared to 2.7 centimeters. Okay, students, it is the definition. It is the certain digits. These are the uncertain digits. The meaningful digits which are known with certainty plus only one uncertain digit are known as significant figures. Okay, students, it is about example. Next one is rules for calculating significant figures. There are 7 rules of there, students. We are discussing one by one. Very important in examination point of view also, in board point of view as well as the JEE point of view also. They will ask very interesting questions are there. We are discussing after completion of these rules. Okay, students, right. First one is first rule. All the non-zero digits are significant. All the non-zero digits present in the result of the experiment are always significant. Example, student, 1947. All the non-zero digits 1947 all are non-zero digits. Hence, there are 4 significant figures. Similarly, students, 123.45 contains 5 numbers. Hence, 5 significant figures are present because all the non-zero digits in the result of the experiment are significant in nature. Now come to second rule, student. The zeros between the two non-zero digits are significant. If the zeros are present between two non-zero digits are always significant. Example, student, 101.1203. 101.1203. Here 1 comma 1 comma 1 2 3 all are non-zero digits other than 0. They are significant. Totally there are 5 significant figures and 2 zeros are present. The zeros are present between two non-zero digits 1 comma 1 and 2 comma 3. These are also significant. Totally 7 significant figures are present in the following number. That is, the zeros between two non-zero digits are significant. Next, students, the zeros present before the first non-zero digit not significant. The zeros present before the first non-zero digit are not significant. For example, student, 0.00052 contains how many significant figure? Means according to the concept, it is the first non-zero digit. In this total number, the first non-zero digit is 5. Before the first non-zero digit, all the zeros are not significant. Therefore, 5 comma 2 are the significant figures. Here, these 3 zeros are not significant, student. It is this the zero present before the decimal point are also not significant. Why? Because this zero just indicating the decimal point only. Okay, student, once again, the zeros present before the first non-zero digit are not significant. Example is 0.0052. These 3 zeros are not significant, hence 2 SFs are present. 2 significant figures are present. Copy, students. Okay, students, next continuation. Rule number 4. According to rule number 4, the zeros present at the right side of the decimal point are always significant. In a number, if the zeros are present at the right side of the decimal point are always significant. For example, student, 12.2300. Here the zeros are present and again they are present at the right side of the decimal point, hence they are significant. And 1, 2, 2, 3, these 4 numbers are non-zero digits. These are obviously significant. 4 plus 3, 7. 7 significant figures are present. All the non-zero digits significant. According to rule number 4, the zeros present right side of the decimal point are always significant. Totally 7 significant figures are there, students. 7 significant figures are present. Next, students, rule number 5. When a number is written in scientific notation, the number of digits between 1 to 10 gives the number of significant figures. When any number in the form of scientific notation, that is n into 10 to the power of n, then the number of digits between 1 to 10 in the scientific notation are called significant figures, are considered as the significant figures. For example, student, 4.01 into 10 square. In this, the numbers between 1 to 10 is 4.01. These are the significant figures. We know that 4, 1 are the non-zero digits. They are always obviously significant figures. And according to rule number 2, the zeros present between the two non-zero digits are always significant. 4, 0, 1. Therefore, 3 SFs are present. 3 significant figures are present. And this 10 square we are not considered. That is, students, when a number is written in the form of scientific notation, the digits present in capital N, that is 4.0n, are called the number of significant figures. Okay, students, right. Next, rule number 6. The zeros present at the end of the number but not at the right side of the decimal point are not significant. Here, student, the zeros are present at the end of the number but not at the right side of the decimal point are not significant. For example, student, 100, the zeros are present at the end of the number, but is there any decimal point, student? No decimal point. Hence, these two are not significant. The two zeros are not significant. One is the significant figure. Only one is the significant figure. Because students, one technical explanation is also there. 100 can be written as 1 into 10 square. Any problem, student? 1 into 10 square. Here 10 square is not the significant figure according to rule number 5. Only one is a significant figure. Hence one significant figure is present. One significant figure is present. Similarly, student, for suppose 100.0, then it is having again 4 significant figures, student. Why? Because the 0 is the decimal point is present. The decimal point is present. We know the students, the 0 present after the decimal point is significant. The zeros present after decimal point is significant, and this one is also significant. The between the two significant numbers, the zeros present between the two significant numbers are also significant. Once again, student, 100.0 is having 4 SFs, whereas 100 is having only one significant figure, because the difference is we are written 100.0. We know the students, the zeros present after the decimal point are significant. Hence the last zero is significant. All the non-zero digits are significant. One is also significant. Therefore, the zeros present between two significant figures are also significant. According to rule number 1, the zeros present between two non-zero digits are also significant. Even though it is 0, but it is significant. Hence, these two zeros also significant. Therefore, 100.0 is having the 4 significant figures 1, 2, 3, 4. 4 SFs are present. For this one, the proof is also there. That is, students, this 100.0 can be written as 1.000 into 10 square. 1.000 into 10 square. Why? Because, student, according to scientific notation concept, if the decimal point moves towards left by 2 places, then 2 is the power of the 10. That is 1.00. Already 0 is there. By if the decimal point moves towards left by 2 places, then 2 is the power of the 10. According to rule number 4, in a scientific notation, the numbers present between 1 to 10 are significant, and the zeros present after decimal point are always significant. 1, 2, 3, 4. Therefore, 4 significant figures are present in the 100.0. In this way, we can explain, and in this way, it also explain, student. In board point of view, they will ask like this, student, how many significant figures are in 100? Absolute answer is 1 significant figure. How many significant figures are present in 100.0? Absolute answer is 4 significant figures. Next one, student, exact numbers are having infinite number of significant figures, because the reason is exact numbers. For suppose 20 pence, there is no chance for 20.15, 20.25, 20.75. That pence can count 1, 2, 3 like that. 20 pence are there. That result will be accurate, 100% accurate. Why? Because there is no error, there is no uncertainty. That numbers are called the exact numbers. All the counting numbers are called the exact numbers. These exact numbers are having any error, any mistake, any uncertainty in that measurement. All these exact numbers are having infinite number of significant figures. It is not 1, 2, 3. Many number of significant figures are present to indicate that they are called as exact numbers are having infinite number of significant figures. Why they are having infinite means this 20 can be written as 20.0. Again 20.00, again 20.000. Like this you will write here 20.0 means 3 SFs. Why? Because the zeros present after the decimal point are significant. The zeros present after decimal point are significant, and this 20 is also significant. Totally 3 significant figures are present. Similarly, the zeros present after decimal point are significant. These zeros are significant, this 2 is significant. Between the two significant figures, these zeros are also significant. Hence, 20.0 is having 3 significant figures. 20.00 is having 4 significant figures. See, students, all the rules once. Therefore, totally rule number 1 to rule number 7 we are given. After completion of this class, we can take screenshot these 7 rules, revise 2 or 3 times, students. Total rule number 1 to rule number 7. Okay students, continuation. Significant figures definition is completed. The rules for calculating for significant figures is completed. Next one is rounding of numbers. Rounding of numbers. What is meant by rounding of numbers? Generally we know that in the marks 24.5 round off to 25, 26.5 round off to 27. The basis for that round offing is now we are discussing here. Why this concept is introduced means for this purpose. The result with certain digits, the result with a certain number of significant figures is reduced to required number of significant figures by using rounding of numbers. The result with certain number of significant figures reduced to required number of significant figures by using rounding of numbers. For example, in some experiment they are mentioned rounding of the following numbers up to 3 significant figures, up to 4 significant figures. Then in that cases we are using this concept, that is the result with a certain number of significant figures is reduced to required number of significant figures by using one concept that is known as rounding of numbers. For example, student, here 3 rules are there. Rule number 1, 2, 3. The first rule is if the last digit to be dropped is greater than 5, then the preceding digit is increased by 1. While rounding of the numbers, if the last digit to be dropped is greater than 5, that is 6, 7, 8, 9 like that, the preceding digit increased by 1 unit. Here student, 7.136 has 4 significant figures because all are non-zero digits. That 4 significant figures can be reduced to 3 significant figures by using rounding of numbers. This last digit 6 can be dropped, but the preceding digit 3 is increased by 1. The preceding digit 3 is increased by 1. Why? Because the 4 significant figures can be converted into 3 significant figures by dropping one digit. If you want to drop the last digit, if it is greater than 5, such that the preceding digit increased by must and should 1. Why? Because according to concept, if the last digit to be dropped is greater than 5, then the preceding digit is increased by 1. Here 4 significant figures are there, then you have to convert into 3 significant figures, then the last digit can be dropped, but the preceding digit is increased by 1. Hence 7.14 is the rounding of 7.136. Here 4 SFs are present, here only 3 SFs are present, 3 significant figures are present. Okay students, next one. If the last digit to be dropped less than 5, then the preceding digit does not changes. Here 7.134 has 4 SFs, 4 significant figures. That can be reduced to 3 SFs, 7.13. The last digit is dropped, but it is less than 5. The preceding number does not changes. Students. Clear student? If the last digit to be dropped is less than 5, then the preceding digit does not changes. 7.134. That 4 is the less than 5, and the preceding digit is retained. It does not changes. 7.134 has 4 SFs, 7.13 has 3 SFs, that is 3 significant figures. Similarly, last rule student, if the last digit to be dropped is exactly 5, that is it is not less than 5, it is not greater than 5, it is exactly 5, then what happens? Then the preceding digit increases by 1. If it is an odd number, the preceding digit does not changes if it is an even number. For example, student, 6.35, it is exactly 5, it is not less than 5, it is not greater than 5, but the preceding digit is that is the digit present before the last digit is called preceding digit, that the preceding digit is 3, but hence it can be increased by 1, 6.4. Here 3 SFs are present, here 2 SFs are present. If the last digit to be dropped is exactly 5 and the preceding digit is even number, it does not change. 6.2 is the the rounding of number. 6.2 is the rounding of number. That is, if the last digit to be dropped exactly 5, then the preceding digit, if it is an even number, it can be increased by 1, and the preceding digit does not changes if it is an even number. Since 3 is the odd number, increased by 1, 6.4 rounding off. Since 2 is the even number, 6.2 is the rounding of a number. These are the three rounding of rules, students. One is the greater than 5, one is the less than 5, one is the exactly 5. In exactly 5, two cases are there. That is the preceding number, even number, or preceding number is the odd number. Okay, students. In the NCERT textbook, in the rounding of numbers, some examples are there. You will practice, students. Next class we are discussing about the arithmetic using multiplication, division, addition and subtraction. From that they will ask one question, students.